Okay, so here we are. This is for any ballistic pendulum group. Um, it, I created this recording and tweaked up this spreadsheet in the context of yesterday, October 13th, 2022, my 1100 class. 'Cause I think I made a mistake in the algebra on the board. Plus, I've now remembered that with this spreadsheet that I handed out to you, and this is different looking now. The spreadsheet I provided, and I think this might be, yeah, that was made during COVID, and we used a simulation. That's why you see speed 1, 2, 3, because I had them choose to do. I asked them to do 3 different speeds because it was very easy to do when it came to a sim. But we should actually though keep what speed do we choose? And I don't. In this one, I'm not sure what it would coincide with. Maybe I'll call it just speed 2, meaning the cocking position of your apparatus. It doesn't matter for your individual analyses, but it's just interesting for me to see what are the 3 different speeds, and it turns out that this mechanism we're using is new. I used it for the first time in the spring semester, and I look back and I noticed that I don't have some data from those runs last semester. I don't know why, but be that as it may. So in class yesterday, I mentioned to the students that that it's a good idea to keep track of a bunch of things and things that don't change, for example. And so, and also we should check nomenclature because at least in the 1100 lab, they use different variables here. So I used in class V of the bullet instead of V sub 0, and I used V system instead of capital V. I stayed with little m and capital M. It is a little tricky making subscripts in Excel. It's one reason, but anyways. But I did stick with delta H, little delta H, and one other difference, height of the table, the lab uses capital H, and I use little h sub t, capital T. You'll forgive me, I just should have checked this thing beforehand. Derive an expression for the fraction, yeah. That's something, since we didn't talk about it in class, that don't worry about it. Physics 1100. I gotta go check. I'll check the 1570 manual and the 2100 manual. But one of the things about this that I was goofing on was making a mistake about was also the analysis of your plus minus, but we'll get there. So you see the height of the table, the mass of the ball, the mass of the pendulum, and because Excel can be a little tricky to enter in long formulas because you just get the single line up above here to enter stuff, I decided to create little m plus capital M, little m plus capital M over M, and that's because I knew I was going to need that variable. If you look over here, and that might have been a mistake. I know I ended up with an m squared in there in 1100 yesterday. Then L here, the length of the pendulum, the acceleration of gravity. And I can also use this equation here, which is the square root of 2 for the time. I'm going to pause this for a minute. I'm going to get my stylus ready. I'll draw the equation. Hold on. Well, you won't notice any difference other than maybe the screen jumping a little bit. But where is the mouse? And so something's wrong here. Okay, I'll pause one more time. All right, it screen jumped again. So, now it decided to quit again. Oh, interesting. Oh, maybe because I got to click on the spreadsheet. There we go. All right. So I was saying how we have this equation for the height and of the table plus v sub 0 y times t plus 1/2 gt squared. And since we're going to go and bring this y sub 0 over to the left side, that becomes delta y. And then this is 0 because we set it up that way. And so this equals 1/2 gt squared. So then t squared equals 2g over delta y. And then t equals the square root of 2g over delta y, which happens to be the height of the table. And it's the square root of the whole thing. So then if we take a look over here, and why don't we just zoom that in for a sec, hold on. And now we can see it's square root of 2 times d2, which is the height of the table, divided by d8, which is the acceleration of gravity. Now, I did this up. This was originally all done in meters, but I told people it was okay to use centimeters and grams. So I've set up both. So of course the time is the same, which you expect it to be. Think about that one for a minute. But it has to be the same, whether you express it in meters, kilograms, seconds, or centimeters, grams, second, CGS system. Mother Nature never lies, or she doesn't care what your science says. She does what she does. So anyways, let's see now. There's stuff on the right. Oops. The stuff on the right there is a holdover, and we don't really need to worry about it. Let's see what happens if I do zoom. Yeah, not a lot of difference. Okay. So anyways, there's my table of all the things that don't change, plus a couple of additional calculations. So in class, you recorded a set of ranges, and you recorded a set of degrees. So the ranges for when it's a projectile, and the degrees is when you use it as a pendulum. So then the pendulum in the projectile, to get the speed of the bullet, we just used this equation was in the manual, and then this is it derived, and we, instead of capital H, we used H sub t, and you notice it's just swapping r and v sub 0, and it's basically bringing the square root term over to the other side. And notice when you do that, you invert it, and we talked about that a little bit in class. And so there it is in centimeters per second using h of t and the gravitational acceleration in centimeters per second and centimeters. And then I did it in meters to get meters per second using the height of the table in meters and the acceleration of gravity in meters per second squared. And so ultimately the answers are the same, except the decimal place is moved. And of course, after I construct the equation, I drag it down with the fill handle. And there we go. Now, one thing I forgot to mention yesterday was the average. Of course, that is our value that we quote. And then we have the standard deviation of the sample. And then the standard error. And instead of dividing by square root of 5, I once again used this count function, because this way, if I had done 6 measurements, I wouldn't have to change anything, because it would just know that I did 6 measurements if I use count. At most, what I would have to do is, with this red rectangle, this red selection box, I would move it around to make sure I was covering everything. And then our percent error is just the fractional error times 100. And we're not surprised that, since this is done with a simulation, that we get a very small percent error. So don't be worried that if you get a much larger number. You should. You most absolutely should get a larger number than that. So don't worry about it. And many people use position 3, so they got ranges on the order of 200 centimeters, right? So this is a different speed setting. Okay, so now we go over to the use of the pendulum. And first of all, let's make sure I think I made an error yesterday in algebra. I know I did now, because there was something about canceling out an m plus m that I missed. So you start off with the momentum. Give me a minute. Right, so this was from the conservation of momentum here. Conservation of momentum. So we had the momentum before, the momentum after. And this one, the next equation is from conservation of energy, but not mechanical or kinetic energy. The kinetic energy is not conserved, but the total energy is. So that was the one where it's K1 plus U1 equals K2 plus U2. And our ballistic pendulum is set up so that when we when the bullet hits the pendulum, we say that is the place of zero potential energy, and it's all kinetic energy right here on the left. Right on the left, right? Over here on the left side of the equal sign. And then when the pendulum reaches its highest point, then it turns around. So briefly, its kinetic energy is zero, and it's all potential energy, which is the mass, the total mass, times the acceleration of gravity, times the change in height from the zero position. So right off the bat, that means that since m plus m is on either side of this equation, both above the dividing line, if there was a fraction involved, I'm allowed to just simply cancel them out. So I'm left with v system squared equals g delta h. Now, of course, that's not, of course, we could get the velocity of the system squared, and that would allow us to calculate the kinetic energy, as you see on the right here. But I never mentioned that in class, so at least in 1100, so we're not going to do that. And we didn't mention it in 1570 either. And now when I think about it, at least 2100, fall of 2022, we also didn't mention it. So anyways, I've got now, I can take the half and bring it over to the right side, because I want v cis on the left all by itself, and then I take the square root, and that's an expression that tells me what v cis is. And yeah, again, I could calculate it, but I don't need to bother. I could just use that to substitute back into the momentum equation. Remember from up here, I just recopied it down here. So I substitute this into here to get this expression. And I want v bullet on the left all by itself, so I just divide by m. So I'm almost certain this is different than class. Yeah, I know it is in 1100 anyway. So, and that's also why up here I decided to calculate little m plus capital M divided by little m. Notice that they come out to be the same thing, right? Which makes sense because the units divide out. It's a dimensionless number, so the ratio has to stay the same. And I have the length of the pendulum in centimeters and meters. And so I go here, and I have my degrees. And remember, we decided how to get, or I went over how to get the L from the angle. And remember, you start out with the pendulum at the rest position. And I know that this distance here is L. And I just want to leave room here. So the total is L. And I'm just going to arbitrarily say I'm going to split it into two pieces, A and delta H. And then I know that when we measure theta, it's at the extreme when it turns around. And now I stipulate that H is a perpendicular line from the vertical position over to the center of mass here. And then we notice that, and then this is L again, because the pendulum doesn't change length. And here I use capital L. But we notice then that A over L is adjacent over hypotenuse equals the cosine of theta. And remember I said earlier that L equals A plus delta H. So that tells me that delta H equals L minus A. And this next expression with the cosine tells me that A equals L cosine of theta. I just want to get out of my way this old notation. Whoops. Okay. So then at the end of the day, delta H equals L minus A equals L minus L cosine theta, which we can conveniently go to, L times 1 minus cosine of theta. And remember, I was starting to get into these complicated equations about propagating error, but we don't need to do any of that. We don't need to write down a theta plus minus theta because we know our statistics, our stat and probability, probability and statistics. And in any event, first of all, let's just finish the basics here. So we get an H for each angle in centimeters, also in meters. And then I can use my formula over here. So D6 is my little m plus capital M divided by little m, and the acceleration of gravity, and the delta H to get in centimeters per second. And then I just use the equivalent MKS numbers to get meters per second. Drag handle, the fill handle, I get, all of them. And then once again, I get the average, standard deviation of the sample, and the standard error. And I get my percent error which is just the fractional error divided by the square root. It's the fractional error times 100. And then we go here, and let's see, I have to clean this up a little bit. Let's turn this into a picture. Cut and paste. Makes it much easier to move it around. And similarly for this calculation. And there we go. Cut and paste this picture. Yeah, much easier to move around, move it bigger or smaller. Okay, so I could probably place this a little better, but remember we discussed it in class that if I take the difference between them, and I just use absolute values so it's positive, and I divide by the average value times 100, that tells me that's the standard way of saying the percent difference. Notice for average, since the two of them are not next to each other, I type the word average. Well, let's do it again just to show you. So then I say I want to average this number, and then I just put a comma because they're not next to each other at that number. And there it is. And that's cool. Okay, the difference. Oh, yeah, it's smaller than the two error bars. So that means that I can believe what I did here. Because if I overlap the two numbers, they still fit within each other's error bars. And that means that I've demonstrated that the ballistic pendulum is a viable tool. Okay, so I'll stop this and get it up onto YouTube and send it out to you guys. See ya.